Welcome back to our documentary explainer series, Inside Time Series. Let's jump right in, because today we are tackling the central mystery and honestly, the biggest paradox of classical forecasting. You see, we spend all this time building these incredibly sophisticated mathematical models to predict the future, right? But there is a massive contradiction at the very heart of how almost all of these classical models actually work. They rely on a secret, hidden rule.
To really wrap our heads around this paradox, let's look at a practical scenario. Imagine you're forecasting electricity demand for a major city. Let's say last year, the demand averaged 5 gigawatts. Then this year, it suddenly averages 8 gigawatts. And next year, it leaps to 12. If the very baseline of our reality is constantly shifting beneath our feet like that, how can an algorithm possibly keep up? I mean, can a model actually learn stable patterns if the world itself never stops changing?
Well, the short answer is they struggle big time because our world is intensely dynamic. Just look around us. We're constantly dealing with things like exponential population growth, the relentless march of inflation, aggressive business expansion, shifting climate patterns, and, wild stock market bull runs. The world literally never stops changing. And yet, many of the classical forecasting models we rely on quietly operate under this massive assumption. They secretly assume that the underlying process generating the data never fundamentally shifts.
And that brings us to the crucial point, stationarity. Now, I want to be super clear here. Stationarity is not another forecasting algorithm. Let me say that again, because it's a really common misconception. It is absolutely not an algorithm. Instead, stationarity is the essential hidden assumption that actually makes our classical models function. It is basically the assumption that time, mathematically speaking, stands still.
Chapter 2. What does stationary really mean?
Okay, let's strip away the heavy math for a second. Set aside all those complex Greek symbols and just focus on pure intuition. Notice the visual contrast we're looking at here. Imagine a time series that's a deterministically trending process, essentially a wild line that's constantly marching upward, maybe tracking that exponential population growth we just talked about. Compare that to a covariant stationary process. Sure, it fluctuates, but it hovers around a stable, constant level. To a forecasting model, that wild trend is just unpredictable chaos, because the baseline is always on the move. But the stationary process, that is mathematically readable. It plays by a consistent set of rules.
So to be considered stationary, specifically what statisticians call weak or covariant stationarity, a time series needs 3 core properties. First up, a stable average, or mean. Basically, the data doesn't wander off into the stratosphere over time. Second, stable variability, or variance, meaning the swings up and down don't suddenly get massively wider or tighter. And third, stable relationships over time, known as autocorrelation. This just means the way today relates to yesterday is exactly the same as the way next Tuesday will relate to next Monday. Ultimately, the goal here is pure statistical consistency.
And this brings us to a really beautiful realization. Stationary does not mean no movement. We aren't looking for a perfectly flat, dead line here. As this quote perfectly captures, stationarity is all about statistical consistency. The data can dance around, it can jump, it can drop, but the rules governing that dance must stay exactly the same over time.
Chapter 3. Making Time Stand Still.
So we know the real world is messy and trending, right? But our models desperately crave that beautiful, stable stationarity. This gives us quite the engineering problem to solve. How do we bridge this gap? How on earth do we take dynamic, non-stationary real-world datasets and mathematically force them into a format that our rigid, classical models can actually read and understand? Well, we have to step in and transform the data ourselves. Take a look at this quarterly population data of Australia, which brilliantly illustrates the problem. It is a textbook deterministically trending process. It just goes up, up, and up. If you were to feed this raw data into a standard autoregressive model, the model would completely break. It would try to assume the average is constant when it clearly, obviously, isn't.
But check this out. This is the exact same population data, but we've applied a mathematical transformation called detrending. Suddenly, that relentless upward climb is entirely gone. What we're left with is just the residual, the noise, and the subtle fluctuations around the stable, flat centerline. We've taken that wild, trending data and successfully tamed it into a stationary format.
It turns out,
Data scientists actually have a whole toolkit to forcefully reveal these hidden stable patterns, kind of like photographic filters, but for math. The most powerful tool in the box is differencing, which simply means subtracting today's value from tomorrow's value, so we only look at the step-by-step changes. We can also detrend to remove long-term shifts, just like we saw a second ago. We can remove seasonality to average out those predictable cycles, like higher sales every December. And we can use log transformations if the variance, the volatility of the data, is expanding over time. By applying these filters, we essentially freeze our changing world into a perfectly stationary snapshot.
Now, you might be wondering, how do we actually know if our transformations worked? For that, we use the Augmented Dickey-Fuller, or ADF test. You can kind of think of this as a mathematical polygraph test for our data. It checks for something called a unit root, which is a really strong indicator of non-stationarity. If the ADF test confirms our p-value is low enough, our data passes the polygraph. We've successfully achieved stationarity.
Chapter 4. Why Engineers Care.
Let's step out of theoretical statistics for a minute and into the real world, because getting this wrong has absolutely massive consequences. Whether you're forecasting retail inventory, energy grid loads, or financial markets, your models will fail spectacularly if you feed them non-stationary data. Engineers spend huge amounts of time building complex data pre-processing pipelines just to detect non-stationarity and monitor changing distributions. Think about it. If a machine learning pipeline completely ignores stationarity, it might try to predict next year's energy demand using a baseline from a decade ago. That is a guaranteed recipe for catastrophic, unreliable forecasts.
You'll probably recall from our earlier explainers the two main pillars of classical forecasting. We have autoregressive models, or AR, which predict future values based on past values, basically capturing momentum. And we have moving average models, or MA, which predict values based on past forecast errors, capturing sudden shocks. But here is the fatal flaw they both share. They completely crash on non-stationary data. For them to work, they absolutely require the rules of the game to remain constant.
Chapter 5. The missing piece.
So, we've seen how the combined ARIMA model works, but now we know its fatal flaw. It just cannot directly handle a changing world. But follow the logic with me here. What if we could take our raw, non-stationary data, transform it into stationary data using our differencing tricks, and then apply the powerful ARIMA model to that clean, stationary dataset? That exact logical breakthrough gives us the absolute crowning achievement of classical time series analysis, ARIMA, autoregressive integrated moving average. You see that mysterious I in the middle? It simply stands for integrated, and all it represents are the differencing steps we apply to the data before fitting the AR and MA components. ARIMA is literally a model that builds the stationarity fix right into its very core.
And doing this unlocks a massive shift in perspective. As this quote highlights so well, the future wasn't impossible to predict. We were simply asking the wrong questions about the past. By understanding stationarity, we stopped asking our models to predict a constantly moving target, and we started asking them to predict the underlying, stable changes between the steps instead.
Well, we have officially laid the groundwork. We've solved the mystery of the hidden assumption. Next time, on Episode 7, we're going to combine everything we've learned, autoregression, moving average models, and differencing to meticulously construct one of the greatest forecasting algorithms ever created, the ARIMA model. But before we go, I want to leave you with a final, pretty provocative thought to chew on. We've learned today that classical models need time to stand still, and we know we can fake it with differencing. But what happens when the real world experiences a sudden, massive paradigm shift? What happens when the fundamental rules of the system change faster than we can actually mathematically difference them? Think about that for a bit, and I'll see you in the next explainer.